Minimization in digital logic. Minimization in digital logic is a technique used to simplify Boolean expressions or logic circuits. The main goal is to reduce the number of logic gates or components required to implement a given logical function. By doing so, the circuit becomes more efficient, faster, and consumes less power. Importance of minimization. Minimization is crucial in digital circuit design for several reasons. Cost effectiveness. Simplified circuits require fewer components, which reduces manufacturing costs. Power efficiency. Fewer gates mean less power consumption, making devices more energy efficient. Speed improvement. Simplified circuits generally have shorter signal paths, leading to faster operations. Reliability. With fewer components, the chances of faults or failures decrease, making the circuit more reliable. Methods of minimization. There are various techniques for minimizing Boolean expressions or logic circuits, each with its own approach and applications. Boolean algebra. Boolean algebra is a mathematical approach to simplify Boolean expressions using a set of rules and laws. Some key laws include identity law, a plus 0 equals a and a 1 equals a, null law, a plus 1 1 and a 0 equals 0, idempotent law, a plus a equals a and a equals a, complement law, a plus a equals 1 and a prime equals 0, distributive law, a b plus c plus ac. By applying these laws, complex Boolean expressions can be reduced to simpler forms. Karnaugh Maps. A Karnaugh map, K-map, is a visual tool that helps simplify Boolean expressions, especially when dealing with up to 6 variables. It is a grid-like diagram where each cell represents a possible combination of input variables and the corresponding output. The primary steps in using a K-map include mapping. Plot the given Boolean function on the K-map. Grouping. Identify groups of ones that can be combined in groups of 1, 2, 4, 8, etc., forming rectangles. Simplifying. Derive the simplified Boolean expression from these groups. K-maps are especially useful because they provide a systematic way of finding the minimal expression without manually applying Boolean algebra rules. Quine-McCluskey method. The Quine-McCluskey method is a tabular approach for minimizing Boolean functions. It's more algorithmic and can handle more variables than K-maps, though it may become computationally expensive. The process involves listing minterms. Start with a list of minterms, combinations of variables where the function is true, prime implicant generation, combine terms with a single bit difference to form prime implicants. Prime implicant table. Construct a table to find the essential prime implicants. Simplification. Choose a minimal set of prime implicants to cover all the minterms. This method is often used in computer-aided design (CAD) tools for circuit simplification. Real-life use case and example. One real-life application of digital logic minimization is in the design of microprocessors. Microprocessors are the brain of computers and many other electronic devices. They need to perform millions or even billions of operations per second. If the logic circuits within a microprocessor are not optimized, they will consume more power, generate more heat, and perform operations more slowly. For instance, when designing a control unit within a microprocessor, Boolean logic is used to create decision-making circuits. By minimizing these logic circuits, the microprocessor can execute instructions more efficiently. This is crucial in portable devices like smartphones, where power consumption and heat dissipation are critical concerns. Conclusion. Minimization in digital logic is an essential step in the design of efficient, cost-effective, and reliable digital circuits. By using techniques such as Boolean algebra, Karnaugh Maps, and the Quine-McCluskey method, complex Boolean expressions can be simplified, leading to optimized digital systems. These methods not only reduce the number of logic gates, but also enhance the overall performance and reliability of electronic devices. Whether in microprocessors, communication systems, or any other digital device, minimization plays a crucial role in ensuring that technology is as efficient as possible.